Okay, back again, and just to mention about the density of water. Water is, of course, a very common and very important substance. In chemistry, in fact, water is known as the universal solvent because it's used as a solvent that is, a medium in which you can do a reaction for so many different things. And there are so many different things that will dissolve in water. So it's kind of an important substance. It's also an unusual substance. And so it bears having, for us to have a little look at the density of water. At room temperature, which is usually defined as about 25 degrees Celsius, even though 25 Celsius is actually about 77 Fahrenheit, which is a pretty warm room. But anyway, I don't know why they use that. But anyway, at room temperature, the density of water is not exactly, but it rounds off to 1.00 grams per milliliter. And in fact, this is the way the metric system was set up. As I said, they really thought about things when they set up the metric system, and water was one of the things they used as their sort of their standard for what the units would be. So 1 gram of water is the mass of 1 milliliter of water. 1 milliliter of water is the volume that has a mass of 1 gram. So that's basically how they define grams and milliliters in the metric system. So this is a pretty easy density to remember. And for other densities, of course, you can always look them up, but water is easy enough that you should actually be able to remember that. Water is interesting because as the temperature goes up, the volume of water will expand, and the density, which remember is mass over volume, decreases. As you would expect for any material. Because if the number on the bottom of the fraction gets bigger, dividing by a bigger number gives you a smaller result. So as temperature goes up, the density definitely should decrease. As temperature decreases, the volume of water contracts and the density increases until 4 degrees Celsius. If you go below 4 degrees Celsius, though, the volume starts increasing again. And the density decreases. And it decreases even more once the water freezes. And the density of ice is about 0.92 grams per milliliter compared to the density of liquid water at 1 grams per milliliter. So water is one of only, the only common substance and one of only a handful of substances of any kind where the solid is more dense, or is less dense, than the liquid. If you think of anything else that's commonly available that can be had as a liquid or a solid, it's always the case that the solid is more dense than the liquid. If you look at something like butter, you take a stick of butter and measure its mass and volume and find out what its density is when it's fresh out of the fridge, when it's a solid. and then you let it sit on the stove and melt, and you take its density again, you'll find that it's less dense as a liquid than it is as a solid. If you take something like, I don't know, steel, and check the density of a piece of steel that's sitting there cold, on the ground as a solid, and then put it in, a blast furnace and melt it, and check its density again once it's molten as a liquid, you'll find that the liquid is less dense than the solid. But actually, water is just the opposite. The solid is less dense than the liquid, and that's why ice floats, because it rises to the top because it's less dense. Which is actually kind of lucky when you think of it. If ice sank, then wintertime would be much more disruptive to aquatic life than it is. If ice started forming at the bottom of the lakes and rivers, all of the plants at the bottoms of the lakes and rivers and seas would die, and the fish that live under there would die, or they'd have to move. Which would be much more disruptive. The way it is with ice floating on top, basically most of the fish and plants will survive the winter. On the other hand, actually the fact that the volume of water gets bigger as it freezes is the reason that frostbite is so dangerous, because our tissues are made up mostly of water, and when that water freezes, it expands, and it breaks through the cell membranes and destroys our cells. And once the cell is destroyed, it's not coming back. It's gone forever. And so, that's why you have to watch out for frostbite, because you can lose appendages that way. All right, so that's density of water. Okay, we could do some examples involving density. So first, let's see here. So what is the density of iron if 7.5 cubic centimeters has a mass of 59.25 grams? Well, this just goes straight to the definition of density. Mass divided by volume. The mass is 59.25 grams, and the volume is 7.50 cubic centimeters. And that would give us 7.5. That would give us 7.90 grams per cubic centimeter. 3 would be the correct number of significant figures here because of the 7.50. And so there you go. Let's see, there's some interesting problems there that we can come back to a little bit later, but we'll do a couple more easy examples first. Okay, so another question could be something like along the lines of, what would be the mass of a 10 cubic centimeter piece of copper? 10 cubic centimeters would be the volume, and we're looking for the mass. And the relationship between mass and volume would be the density. So we can look up the density of copper in tables, or you can Google it or something, and you find out that the density of copper is 8.96 grams per cubic centimeter. And if we want the mass, we need to rearrange the equation for density. We have density equals mass over volume, and we could use our triangle. And we have, remember, mass over volume means that mass has to go on top, and volume goes in one of the bottom spaces, and density goes in the other bottom space. Okay, so if we want mass, we cover up mass, and that means that mass is density times volume. Okay, so density is 8.96 grams per cubic centimeter, and the volume was 10 cubic centimeters. Notice that the units work out, because cubic centimeters will cancel with cubic centimeters, and we end up with grams. And that would be 89.6 grams. All right, so there's another example. Okay, so we can find the mass, or sorry, volume. The volume is what we're looking for. If we have the density of ice, we can use the same triangle to find the volume. If you want to find volume, just cover up volume and see what's left. Mass over density. Okay, so the mass is 5,000 grams. The density is 0.92 grams per cubic centimeter. You can work this out, and it will work out, but I want to show you the units, to show you how to make sure the units work out. Because if you have 5,000 grams divided by 0.92 grams per cubic centimeter, that's equivalent to multiplying by the inverse of what's on the bottom. The inverse of what's on the bottom would be 1 cubic centimeter for every 0.92 grams. And when you do it like this, you can make sure very easily that the units are working out, because you'll notice that grams cancel with grams. And you get cubic centimeters as the unit, and that is what you want as the unit. So 5,000 divided by 0.92 would be 5434.782609 cubic centimeters. So let's see, 5,000. I'm going to put a decimal point at the end of that so that it's 4 significant figures. But even so, 0.92 is only 2 significant figures. So the 5 and the 4 can stay, but everything from the 3 on has to go. 3 is the first number we're dropping. It's less than 5, so we don't have to change any of the numbers we're keeping. But we're dropping 2 digits before the decimal point, so we have to replace those with zeros to maintain the magnitude. And so 5,400 cubic centimeters would be our answer. Okay. So let's see, if you have a 50 cubic centimeter volume, If you have 51.3 grams of a 50 cubic centimeter volume of one of the substances listed in table 1.3, which one is it? Okay, so essentially what you're going to do here is find the density of that object and compare it to the densities in the table. The one that matches, that should be the substance. So let's see. We've got our density table again. Density is mass over volume. We want density, so we need mass over volume. 51.5 grams over exactly 50 cubic centimeters gives you 1.03 grams per cubic centimeter. And that density matches seawater. And so that should be it. Hopefully. Hopefully what you had was a liquid. If it's a piece of metal, then you did something wrong. Okay, you can use this to figure out things like what would be the mass of gasoline in your gas tank, as long as you know the volume of the gas tank. The mass of gasoline, we're assuming as being 0.680 grams per milliliter. In a 94.6 liter gas tank. Okay, so simple enough. If you want mass, it's just density times volume. But the catch here is that the units don't match. You've got density in grams per milliliter, but you've got the volume in liters. And so you need the density, you need the volume in milliliters. Or you could change the density to grams per liter, but that would be harder, so I would recommend changing the volume to milliliters. And so we have 94.6 liters, and there are 1,000 milliliters per liter, or there's 1 milliliter for every 0.001 liter. They mean the same thing. 1,000 over 1 is the same as 1 over 0.001 numerically. I use this version just because it reflects the definition of milli more accurately. 1 milliliter is 1/1000th of a liter, which is 0.001. But you could use 1,000 milliliters over 1 liter, and that would be just as correct. So 94.6 divided by 0.001 gives us 94,600 milliliters. Okay, so now that we got that, we can use our equation. Density is 0.680 grams per milliliter. And we have 94,600 milliliters. And that gives 64,328 grams. Now let's have a look at significant figures here, because that's a little beyond what we should be using. 0.680 has 3 significant figures. The 0 at the end counts because there's a decimal point. 94.6 obviously also has 3 significant figures. And so for 3 significant figures, we can keep the 6 and the 4 and the 3, but the other 2 numbers, 2 and the 8, have to go. The first number we're dropping is a 2, which is less than 5, so it has no effect on the numbers before it. But we're dropping 2 digits before the decimal point, which is right there at the end of the number. And so those have to be replaced with zeros to maintain the magnitude of the number. So 64,300 would be the answer to the proper number of significant figures. You could also report this as 64.3 kilograms if you wanted to, but you don't really have to. 64,300 grams is okay. You know, unless I ask for the answer in kilograms. Okay. Okay, so in this example, we've got a hot dog bun with a volume of 240 cubic centimeters and a density of 0.15 grams per cubic centimeter. Gets crushed into a volume of 195 cubic centimeters. What is the new density of the bun? Well, we know that density is mass over volume, and we've got the new volume. That's 195 cubic centimeters. But what about the mass? What is the mass of the bun after it's been crushed? The thing is, mass is just a measurement of the amount of matter in an object. Crushing the bun should not affect the mass. It should be the same as the old mass. But it doesn't say what the old mass was before it was crushed. And so that means that we're going to have to find it from the original volume and density. Okay, so from the original volume and density, we go back to our triangle. And to find mass, it's going to be density times volume. The density originally was 0.15 grams per cubic centimeter. And the volume was 240 cubic centimeters. So you want the old, the density, the old density and the old volume. Basically conditions that were in effect at the same time. So 0.15 times 240 is 36. And that would be 36 grams. That was the mass then, and it should be the mass now also. So the new density would be the mass, which hasn't changed, divided by the new volume, which is 195 cubic centimeters. So you've basically got the same mass compacted into a smaller area. .36 divided by 195 is 0.184615385. And let's see, for significant figures, 240 without a decimal point is 3. 0.15 is also 3. That's 3. I'm sorry, 2. 240 without a decimal point is 2. 0.15 is 2. 195 is 3. And so it looks like we're down to 2. 4 is the first number that has to be dropped, and that's less than 5, so we can leave the 0.18 alone. And so it's 0.18 grams per cubic centimeter. Notice that, remember that crushing an object, making it smaller, should increase the density. And indeed it did. It was 0.15 to begin with. Now it's 0.19, or 8, sorry, 1.18. So it did get more dense. So that makes sense. Okay, that's an overview of what some of the things you can do with density. There are other things that we can do here. Some of which involve English units and conversions between metric and English units. So the next couple of questions are a little bit harder than what we've been working on, but they're interesting. Oh, so interesting here. Given that the density of water is 1 gram per milliliter, what would be the mass of 1 gallon of water? Okay, we know that from our triangle, like we have up above, that mass is equal to density times volume. Okay, so if we can find the mass, say, in metric units, we could always change that to pounds later. That would be one way of approaching this. The problem is, though, that the volume we're being asked for is in English units. So you either need density in English units or you need volume in metric units. And of the two, it would be easier to change the volume to metric units. So we have the density in metric units. What we need to go with it is the volume in metric units, preferably milliliters, because we have density in grams per milliliter. Okay, so let's look for some conversion factors. 1 gallon, of the relationship between gallons, let's see, under volume, we have 1 gallon is 3.786 liters. Okay, that helps. Because we're starting with 1 gallon, and we can change that to liters with this conversion factor that we just got. And at this point, gallons will cancel out and we'll have liters. If you've got liters, you can easily change to milliliters. Let's see, you need liters on the bottom, and there's 1 milliliter for every 1/1000th of a liter. Or you could say 1,000 milliliters per liter. Either way, should work. So 1 gallon in terms of milliliters would end up being equal to, oh, notice that liters cancel. 1 gallon would be equal to 1 times 3.786 divided by 0.001. So 1 gallon is equal to 3,786 milliliters. So now we can take mass is equal to density, which is 1 gram per milliliter, times 3,786 milliliters, which is 3,786 grams. So the mass of 1 gallon of water is 3,786 grams. Now we just have to change that to pounds. So the relationship between grams and pounds under mass, let's see, 1 pound is 453.6 grams. Okay, grams will cancel out, and we will have pounds. So 3,786 divided by 453.6. And that's 8.34 blah, blah, blah pounds. So let's see about significant figures. Our density had 3 significant figures. I'm going to assume that I meant 1.00 gallons, so that'll have 3 significant figures. Any other numbers we introduced here, that had 4 significant figures. The conversion factor between gallons and liters. This is exact because the conversion between milliliters and liters is entirely within the metric system. And that looks like it. So 3 significant figures it is. 834 can stay, but everything from 6 on has to go. Since 6 is greater than 5, that will mean that the 4 has to become a 5. So that's 8.35 pounds to the proper number of significant figures. Okay, that one was pretty challenging. So if you follow that one, you're doing really well. I've got a couple more of those to do, but I guess we're getting close to our time limit for this segment. And so I'll pick it up next time.